Does anybody have any questions? Any questions?
Sorry.
Yep. Yes. Oh, and you have a question.
Question 4. 1 minute, let me just check. Question 4C.
Let's have a look at that. Question 4C. So go to question 4. Got A, part B, part C. Yep. Is that the one you were looking at?
No, 4E rather.
Sorry, 4E. Let's have a quick look. Okay, yep.
Yeah. Could you please explain it to me again?
Right, this is down to projectile motion. If we think about it carefully with projectiles, I'm going to use a blank piece of paper for this. If we remember our projectile motion physics, there are two sorts of motion. There's if you've got any kind of projectile following a trajectory, let's say it's fired out of a cannon, completely different scenario. The projectile would follow that particular sort of parabolic path. Now, what happens is as it's fired, as the projectile sort of is launched and is falling under gravity, it's launched with an initial sort of velocity v, and that velocity has a vertical component and a horizontal component. Now, if we think about it, that horizontal component has no effect whatsoever on the vertical component and vice versa, okay? Because there's no component of that horizontal component that's in the direction of the vertical component. So if you've got a projectile and we ignore air resistance, the horizontal component is going to be constant. Horizontal component of speed is going to be constant. The vertical component of the velocity, that's going to be changing because it'll be falling under gravity. Because if we think about it, the gravitational forces always act downwards, and because they always act downwards, it only affects the vertical component of the motion. That's a basic concept of projectile motion. Does that make sense?
Yeah.
Okay. Now this can be proven horizontal, sort of practically, but obviously I can't do that very easily at my desk on camera. But basically, if you were to take, there's a classic example which is called the monkey and hunter. It's not very politically correct, I'm afraid. So imagine you've got a hunter with a gun, okay? Or bow and arrow, could be. And you've got a monkey. Can't draw monkeys very well. Try and sort of draw him hang on to a branch. Imagine that monkey is hanging on to a branch, okay? Now, if you take a direct line of sight, a straight line, obviously the hunter wants to shoot the monkey. Now, what actually happens is when the bullet is fired, it's got a horizontal and vertical component of its motion, of its trajectory. So the monkey, let's imagine with this, that the monkey decides to let go of the branch just as the bullet is fired. The monkey will accelerate downwards with the same acceleration as the downwards acceleration of the bullet from the gun. Okay, to be the same downwards acceleration. Okay, does that make sense? So what will happen is that the bullet will follow its trajectory, which I haven't drawn very well, and the monkey will accelerate downwards the same distance, so the bullet will still hit the monkey. Okay, the horizontal component, the fact that there's a horizontal component of velocity, doesn't affect the vertical component of the velocity. Okay, it's why if you if you want to fly, you have to use wings to create a vertical lift. You can't just fly just by going very fast. That makes sense?
So, Gary, what's the answer to the question? Like the exact answer to that particular
The exact
question?
answer to that question, I'm going to find it again. Well, it's the fact that if we look at it, experiments repeated with twice the horizontal speed, okay, describe and explain what effect, if any, this would have on the effect on the data collected. It has no effect. The reason being, if you look at the data carefully, you can see the car's driven off the cliff, which is 10 meters high, so that's not changed. And its height at regular time intervals is measured. So it's nothing to do with its range or anything like that. It's just the height of the car. So really, this part of the question, although the car was moving at 20 meters per second, these values would be exactly the same if the car was just dropped. Does that make sense?
Yeah.
Okay. So it actually has no effect, because if we have any two vectors at right angles to each other, they have no effect on each other.
All right. Thank you.
Okay. Any other questions? Okay, so the last bit we're going to do, I'm going to talk to you a little bit for probably about half an hour, and then I'll set you on a task. I'll talk to you for about half an hour about uncertainties. And because again, although I think we're getting better at working with uncertainties, I think that I think there's still some scope for improvement. The two things that that, as I said before in my sort of when I was going through the last walkthrough, were the ideas about precision, okay, whether or not something's precise, and accuracy. They sound like they are the same thing. They are not. So precision, in terms of a value being precise, it is about how close together repeat values are. Okay. It's also down to a thing called the sensitivity of the apparatus. So in other words, it could be, if you're looking at the precision of a piece of measuring measuring apparatus, it is actually the sensitivity. Okay, so that tells you what precision is. Okay, so for example, we looked before about how close together the values are. So if we had three values that were with three values of the acceleration due to gravity, which should be 9.81. If I had, say, 9.76, 9.77, and 9.75, those three values would be precise because they're very close to each other. Okay? They're not, but if the real value was 9.81, then obviously they're not accurate, because accuracy is about how close the accuracy of a measurement, how close a measurement is to its true value. Okay. The key idea is that with precision, we think about uncertainty. For example, here, if somebody measured the acceleration due to free fall to be 9.76, 9.77 the second time round, and 9.75, they could conclude that they know that value with a high degree of certainty. Okay, because they're all very, very close together. Every time they did the experiment, they got very, very similar values. So there would be a low uncertainty. In terms of accuracy, we think about error. Error, just like as the name implies, an error is to do with something just being wrong. So here we know the true value, well, the average value would be 9.76. Okay. The measured value of G for the average of those three values up there is 9.76. The true value, what it should be, is 9.81. So there is a source of error. Now, where do you get a high error and a low uncertainty, we say that the error is systematic, because something to do with the experiment must have caused this value to be, this value to be very different to this value. Okay, there must be something that's caused it to be different. It could be that the vertical scale used to measure G by free fall was incorrect and was badly calibrated. It could be to do with the procedure that was used, but either way, it was the cause of that particular error. Okay. If you have a low error, so your value is accurate, but a high uncertainty, that's what we call random errors. Okay, because the values, if I measured 9.81, if I measured it to be, say, let's see, 9.61, 10.01, and 9.81 as my three values, they're very, very different. Okay, but if I took an average, they'd average to be 9.81, which is close to the true value. So that would be a low error because it's close to the true value. It'd be an accurate measurement of G, but there'd be a high level of uncertainty. That random error is usually due to something not being consistent throughout an experiment, or by doing measurements manually. Okay, so for example, if you're doing G by free fall, timing with a stopwatch. So that's two things to look out for, is the difference between precision and accuracy. The other aspect to uncertainties is down to, particularly uncertainties, is down to the calculation of them. To get the absolute uncertainty of equipment, oops, I'll try and spell correctly. To get the absolute uncertainty for equipment, then with the equipment, that will be the sensitivity of the apparatus. So for example, if you had a 30 centimeter ruler, if I had a ruler, the sensitivity of this scale here is sensitivity. Okay. The scale here is to the nearest millimeter. Okay, so that's the uncertainty in a measurement of the length of a line, let's say. Okay. The uncertainty in repeat measurements is going to be the maximum value minus the minimum value over 2. Okay, so that's the uncertainty of a piece of equipment. This is the uncertainty of repeat measurements. Okay, so that then gives you, that then tells you about the uncertainty of a measured value. You just got to remember that the uncertainty uses a particular symbol called sigma. It's a lowercase sigma. So, for example, if I want to say measure the uncertainty in time, if I measure the time to be, if I measured two values of time to be 1.1 seconds and 0.7 seconds, then the uncertainty of the time would be 1.1 minus 0.7 over 2, which would be 0.2 seconds. So the time, you'd express it this way. So the time is equal to, well, the average of these two is 0.8 plus or minus 0.2 seconds. Okay? And that would be how you'd express it. To get the percentage uncertainty, you would want to work out the uncertainty and divide it by the value. So in this case, in my example, it would be the uncertainty 0.2 over 0.8, which is 0.25, which is the same thing as saying 25% uncertainty. Okay. So you're looking at working out percentage uncertainty. So imagine I had a particular simple question as an example. Now, if I take this further after the example, if I've got a height h, so well, let's have a constant velocity questions, okay? So the distance travelled by a toy car, let's say, is 2.0 meters plus or minus 0.2 meters. And let's say the time it took, well, let's say it's going to be 0.8 seconds plus or minus 0.2 seconds. Okay. If I wanted to work out the speed of the average speed of the car, the average speed is the total distance divided by total time. Okay. So if I worked out the speed, that would be 2 seconds divided by 0.8. Which comes out to be 2.5 meters per second. Okay. If I wanted to work out the uncertainty, there are two ways of doing this. As I've got two values which are being multiplied or divided, I add together the percentage uncertainty. So to get the percentage uncertainty in the speed, it's the percentage uncertainty in the distance plus the percentage uncertainty in the time. And the simplest way to do this is to do this by stages. So we start with a substitution. The uncertainty in distance was 0.2 meters divided by 2 plus percentage uncertainty in time, which was 0.2 over 0.8. So we end up with, that is 0.1 plus or 10% uncertainty. This one we calculated before to be 0.25. So it's 0.35, which is 35% uncertainty. So to get the absolute uncertainty, because that's the uncertainty divided by the value, all we need to do is work out that the uncertainty is going to be the percentage uncertainty as expressed as a decimal, 35%, multiplied by V, which is 0.35 multiplied by 2.5, which, as I've been doing this as an example, 0.35 multiplied by 2.5 gives me 0.875. Okay. Now, if I look here, if I look very carefully, I can see that actually I've only really got a calculation to one decimal place here. So I want to sort of only have one decimal place here as well. So what I would say is that the speed v is 2.5 plus or minus, well, I'd want to round that off. So I'd say 2.5, meters per second plus or minus 0. Well, I'll round it off to one significant figure, one decimal place, 0.9 meters per second. Okay. So that's one way to do it. Okay. So that gives you the absolute uncertainty. This is absolute. Absolute. This is percentage. So when you're doing a question that involves calculating an uncertainty in repeated values or in any values where you're given the uncertainty, just check which one it's asking you to calculate. Now, the other way to actually do this, if you're ever completely stuck, because there are rules with combining uncertainties. So, for example, if you've got C equals A plus B, all you have to do is add, or C equals A minus B, you add the absolute uncertainties. Oops. Okay. If you've got x equals yz or x equals y over z, for example, then you always add the percentage uncertainties. Okay. So another sort of example you might get is if you've got E equals 4F. Okay, let's imagine you've got E equals 4F. Here, that value of 4 has no uncertainty. So the percentage uncertainty in E is equal to the percentage uncertainty in F. Okay, so you've got the same percentage uncertainties, but not the same absolute uncertainties. The other example you might get is, I'll pick some other letters of the alphabet, N equals M to the power of 3. Well, the percentage uncertainty in N so you've got a power, you multiply the percentage uncertainty by the power. Okay, so you multiply the percentage uncertainty by the power and you get the percentage uncertainty in N. So for example, if I go back, for example, if I said that A is equal to 2 plus or minus 1, B equals 4 plus or minus 1, C would be 2 plus 4, if we add them together, C equals A plus B, which is 2 plus 4, which is 6. The percentage uncertainty in C is simply the addition of the two uncertainties, 1 plus 1, which is 2. So C would be 6 plus or minus 2. If I've got a multiplication, if I've said that if I pick x equals yz, if I said that y was equal to 1 plus or minus 0.5, and I said that z was equal to 2 plus or minus, let's say 0.5 as well. Why not? So to work out the percentage uncertainty in x, Well, we know that x would be 1 times 2, so that would be 2. So what I could then do is work out the percentage uncertainty. So the percentage uncertainty in y plus the percentage uncertainty in z. So the percentage uncertainty in y is going to be 0.5 over 1. So that's 0.5 plus 0.5 over 2, which is 0.25. So that would be 0.75. So 2 times 0.75 would give me 1.5. So x would be equal to 2 plus or minus 1.5. Okay. And similarly here, if I had E was equal to 3 plus or minus 1.2, so I said 3.0 plus or minus 1.2, then F would have the same percentage uncertainties. It would be 1.2 over 3, which is 0.4. So F would be 3 to 4 times, sorry, try again. If I said F was equal to, I do apologize. So I said that E would be 4 times F, so that would be 12. Okay. To get the percentage uncertainty in E, all I do is I work, it's the same percentage uncertainty, 0.4. So the absolute uncertainty in E is 0.4 times by the value of E, which is 12, which is equal to 4.8. So E would be 12 plus or minus 4.8. I might even express it as E is plus or minus 12 plus or minus 5. Okay, and that then gives you your uncertainty. Similarly here, if you've got a value to the power of 3, I think it becomes pretty obvious now. If we said that M was 4 plus or minus 1, okay, so we'd know that N was 4 cubed, which I'd have to work it out, 64. So to get my value of, to get my uncertainty, percentage uncertainty in N, it's going to be 4 times the percentage uncertainty in M. So it's 4 times, the uncertainty is 1, M was 4, so that would be 1, so it'd be 100%. Sounds rather nasty, but it's true. So it would be the fact that N, well, 100% of 64 is 64, would be 64 plus or minus 64, which would be horrendous if it was a real experiment. Okay, so those are ways of calculating the uncertainties. If you're given something a little bit more complex, let's do a worked example of something really complex, and you really don't know how to use those formulae, okay? Because this is a universally acceptable method. Let's say we had A equals cosine theta times the sine of theta, okay? And let's say theta was 30 degrees plus or minus 10 degrees. Really horrendous level of uncertainty here. What we can do is you can work out the maximum and minimum values. So the maximum value of A is when cosine theta and sine theta are both as big as possible. So I happen to know that if we work out the cosine of 30, if we worked out, say, the cosine of 30, whoops. If I made, that would be 0.866. If I made that 30 into a bigger angle, 40, you see you get a smaller number. So I'm looking for, to get a maximum value, that theta needs to be smaller. So we think about it, the range, the maximum possible range of values, 30 minus plus or minus 10 means anywhere between 20 and 40 degrees. So it'd be the cosine of 20, because that would give me the highest possible number, multiplied by the sine. Well, the sine of 30 and the sine of 40. Sine of 30 is 0.5. The sine of 40 is a bigger number. So I'd want to use my maximum possible value. So it'd be the sine of 40 degrees. Okay? And I could work it out. So it'd be sine of 40 degrees multiplied by the cosine of 20 degrees, because 30 minus 10 is 20, would give me a maximum possible value of 0.604. Okay, probably won't use that that many significant figures in my final answer, but I'm going to keep it in my working. My minimum possible value of A, well, the cosine of the angle's got to be as big as possible, so it's got to be small as possible. So this would be the cosine of 40 degrees, which is smaller, multiplied by the sine of 20 degrees. So I work out my minimum value. Cosine of 40 multiplied by the sine of 20 gives me 0.262. So what I then want to do is to get my actual absolute uncertainty. It's my maximum value for A minus my minimum value for A over 2. So we end up with 0.604 minus 0.262. Gives me 3.42 divided by 2 gives me 0.171. Okay, so then I want to calculate what the true value should be. Well, the true value would be if it was 30 degrees. So the cosine of 30 times the sine of 30 gives me 0.433. Plus or minus my uncertainty, 0.171. Well, to be honest with you, I don't really need this third significant figure here, because obviously that just sort of that's been drowned out by the uncertainty here. So I would actually submit my final answer as being 0.43, could even say 0.4, plus or minus 0.17. That then gives you your that's how you calculate an uncertainty. If you don't know how to calculate it manually, just take the maximum possible value you could calculate that it could possibly be, minus the minimum possible value that it could be. Okay, and that's about it. The only thing to remember is in question 1, you're in the context of an experiment. So what you need to do is think about the experiment, think about the size of the uncertainties. If you're looking to improve an experiment, what you're looking for is the largest source of uncertainty. So let's say, for example, we go back to our speed is distance over time. Let's say we want to calculate the speed of something, and we know it's s over t. Let's say the distance was 2.0 plus or minus 0.2 meters, and t was, let's say it's 1.0 plus or minus 0.1 seconds. Now let's pick something a little bit better, 0.2 seconds, let's say. We'll see why. So if we want to calculate the speed, obviously it's 2 meters per second. Okay. Want to calculate the uncertainty. Well, that's going to be 10%. That's 10% of that, so that's 0.1. The uncertainty here is going to be 20%. So the overall uncertainty, when you add the two together, is going to be 30%. 30% of 2 is 0.6. Okay. Now, if we think about it, which one is giving us the biggest error, the biggest uncertainty? The timing is. So when we're looking at the context of an experiment, this factor is giving us twice the uncertainty of the other factor. So if you're looking to improve an experiment, what you're looking for really is a way of reducing your biggest percentage uncertainty, okay? The only difference occurs is if you've got that uncertainty is in the measuring apparatus, then obviously you want to try and go for something a bit more sensitive or a bit more precise. However, if that uncertainty is an uncertainty in a measurement, i.e. from repeats which are very far apart, so it's not very precise readings, it may be the method that you need to look into. So for example, with timing, here I've measured with an uncertainty of 0.2 seconds. If I measured the time 3 times and actually my uncertainty, my measurement was much larger, I'd want to maybe find an automatic way of timing using a data logger. Okay. If the uncertainty in my measurement was the same as the uncertainty in the measuring equipment, then I'd want to go for some more precise measuring equipment. Does that make sense? All okay with that? Right. Okay. So what I'm going to do next, I'm going to first of all, I'm going to ask you if there are any questions. Anybody have any questions? Any questions? You know all about it? Right. Well, don't forget that obviously next week you've got your UFP exams. If you don't have an exam timetable, then what you need to do is make sure you've contacted Mrs. Randon urgently so that you can ask her for your timetable if you don't have your UFP timetable. Remember that the UFP exams next week are in the King's Hall. The only exception are those of you who are out of the country and therefore not on site to take the exam. If you're a day student, then it would be expected that you would be on site you'd be expected to come in. Okay. Any questions? Any final questions? Nothing at all? Okay, what I would like you to do for the last half an hour of the lesson, I'm gonna keep the Zoom open. And what I'd like you to do is really spend a bit of time just going back over your exam papers. I've gone through some of the exam papers, but some of them have been a bit sort of garbled in the scanning of them, and they're not coming through on my computer very particularly well. But I have marked what I could find. I'd like to just quickly go over your exam papers based on what I've just shown you, and just go through the methods, particularly the questions where you felt you weren't very confident with them. Just see if you can remember what I showed you. I'm going to put this up on YouTube in the next sort of 15 minutes or so. So if you spend the first 15 minutes going over your exam paper, by then hopefully you go back into this lesson. There should be a YouTube link, and you can use the YouTube link to watch the walkthrough and also this masterclass. Revision class on uncertainties and precision and errors, which should help you. Okay, everyone. Other than that, well done. I'm going to log out for a second because I need to in order to